Okay, we continue with the second part of this lecture, bioreactor engineering, with this example. Okay, is batch reaction time with enzyme deactivation. Okay, they said that is enzyme is from example previous one. The enzyme has half-life of 4.4 hours for this one. Okay, compare with figure 13.1 or this one. The batch required to achieve 90% of substrate conversion. Okay, 90% of substrate conversion, so it's 3 hours something from this graph, and then we plot, okay, from this equation. Okay, we use the same information from the previous lecture. S0 is 12 millimolar, Vmax 9 millimolar per hour, Km is 8.9 millimole. Okay, SF, because it's 90% conversion, SF is from 0.1 S0 times this one, which is equal to this one. And we have used half-life TH from this equation. Okay, this is first order. Natural log of 2 times TH. Okay, we have KD here, which is 0.158 per hour. Okay, and next, and then we substitute to this one TB from this to this equation. We have everything here already, so we should know how to calculate it. And then with enzyme deactivation, the time required for conversion increase from this one. Okay, from this figure, see, 3 hours something, 3.5 hours to 5 hours from this equation. So mean that if you lost your enzyme during the process, you might need to have more time to get the same conversion of your substrate, which is this example. So if you are not familiar with the calculation, you can pause the video and then you continue the handwriting, for example, and then compare with the text that I give it to you. And okay, if there is some deactivation of enzyme, so you need more time to wait to get the same conversion. We might go to the next one, is culture time. Okay, this is question. Determine the batch culture time to require. Okay, A, produce 10 grams of biomass. B, 90% substrate conversion. C, 100 grams of ethanol. Okay, we read the book. We read the question. Simomonas mobilis is used to convert glucose. Okay, we use glucose to produce ethanol in a batch fermentation under anaerobic condition without oxygen. The yield of biomass from substrate is 0.06 gram per gram. This yield is 7 px products substrate. Okay, we can consider later. It's quite difficult. The maintenance conversion coefficient is this one. The specific rate production fermentation due to the maintenance is 1.1 per hour. The maximum growth mu max this hour. Okay, 5 grams of bacteria or inoculate. Okay, you use as I mentioned, inoculation. Okay, you put some concentration inside. 50 liter of media contain this glucose. Okay, and then we want to find this kind of thing. Okay, we have YXS substrate. Okay, and then this one, and mu max is this one. MS 2.2, this one is MS. MP, this one, and S0, this one, substrate at the beginning. X0 is 5 gram of bacteria liter, this one. Okay, for A, we calculate XF. The final amount of biomass, is this one. Okay, you have XF here. After you have XF 0.3, and then you use this equation, and then you have time is 3.7 hours, and then you use this equation, and then you put this one. For 90% of culturing time, you use this equation. Okay, and then you have 5.7 hours. Okay, if you are not, if it fast, so you can pause the video and then you can put the number here. And QP is 12 point this equation, and batch culture we have mu equal to mu max. Okay, to produce 100 gram of ethanol, which is this one. This is this one. So we have no product at the beginning. And after that, we use okay, this one, this equation. The batch culture time is 3.4 hours. So roughly idea for this one, if you want to produce some ethanol from glucose, and then you use this bacteria, this microorganism to convert. So you have idea that how much time that you need to achieve what you want from your product. Okay, and then sometimes you have this kind of thing, preparation harvest time. So harvest time is this one, when the cell concentration reach the nearly at the nearly reach the steady plateau. I mean, reach the stationary phase. So it at the end of exponential phase, and then you have this thing. So you can harvest your cell at that time. Next, okay, how much we have more? Okay, we have this. Okay, have a look on this one. So what is determine the reactor volume to treat this 18 cubic meter trisocin solution per day. Okay, you need for the industrial, sometimes you need to have the idea how large of your reactor. Okay, from this information you have Km, which is this one, Vmax, and R, diffusibility, S1, convert, feed 4. Okay, you have this kind of idea. Okay, mushroom tyrosinase. Okay, this is enzyme, is immobilized. So it's encapsulate, immobilized in 2mm sphere bead. Okay, for conversion. Okay, this toxic tyrosine to DOPA in a continuous well mixed bubble column. Okay, they use bubble column. The Mihaly constant from immobilized cell is 2, and this km. Solution contain this 15 gram mole per cubic meter. This is tyrosine. It's fed to the reactor because of high cost of substrate. The desired conversion is 99%, so you need to convert this. So the remaining tyrosine is 1%. Reactor is loaded with a bead. Density of this one. This is how much you use the bead. Okay. All enzyme is retained with the reactor. Vmax for immobilized is this one. And per cubic meter of bead. Okay, they use a lot of bead. Effectiveness diffusibility is this one. 7 times 10 to minus 10. This one. External mass transfer negligible. Where. Okay, you need to determine volume of the reactor. This one. Okay, you just follow this calculation maybe. F, okay, you transfer to this one. Cubic meter per second. Okay, you just use this one. This convert this to per day to meter. For 99% conversion. Okay, blah. So we can refer to this section, the thief modulus. So this form heterogeneous reaction, okay, is 1.19. From this figure, we have this thing. This is called diffusibility. What else? Not sure. So you can check the book as well. Not sure what is going on. So I will give you the answer of this one from about this area. Okay, and then so we have diffusibility here. Okay, diffusibility, and then we will put something here as well. Okay, so roughly for this this example, you need to have how large of your reactor, of your bubble column, Okay, for this one should be the last example. Okay, it's the same thing. This one, Simomonas mobilis. Okay, from this previous example in chemostat culture, so you use to control the temperature. In this very large, this is very large, 60 cubic meter fermenter. The feed contain glucose. Ks is 0.2. Okay, so we need to calculate what flow rate. Okay, should for this one, and what flow rate is cell density, and what flow rate of A, and what flow rate of ethanol is produced. This we use the same information from the previous example, and we identify the D, okay, which is this one, 0.26 per hour. From this one, F times D, this volume, okay, is this one. Okay, this from the beginning. Okay, and next, okay, this is the flow rate of steady state substrate is 1.5 gram per liter. Gram per liter is 15.6 cubic meter per ounce. The cell density is this one. Okay, you put in this equation, you have 0.42 gram per hour. And then this is the steady ethanol concentration. You have gram per liter. And again, if it's very fast, so you can pause the video and then have a look from your calculation again, and then sometimes it's linked together. Okay. And for the last section, we need to talk about sterilization. And we have liquid sterilization. We have batch heat sterilization. When you have some liquid inside, you can have batch process like similar to this one, and then you put in the autoclave, and then you have a very clean liquid. And sometimes we have heat sterilization of liquid, and sometimes we use filter to sterilize of the liquid. And we need to sterilize the air as well, because sometimes the air is very what is called, it can cause some contamination into your system as well. This is how they use liquid. So you heat from the temperature to basically is 121 degrees Celsius, and hold as some period of time. And then sometimes you have to apply some pressure here as well, because the temperature of the water cannot reach beyond 100. So you have to put like 15 pound per square inch pressure as well. And after that, you let your liquid cool down, and then you use the liquid after that. This is number of cell that you eliminate. Okay, so everything is die already. This is final. It's very small amount of cell after you are sterilize of your liquid. I mean, this is contamination cell, so you just get rid of everything inside the liquid. And sometimes you use heat exchanger. This one continuous injection fast cooling. This one is heat exchanger. This one is fermenter, but you sterilize your liquid continuously to your fermenter. Okay. This is steam inject to the system, and then you have your sterile media as well. Sometimes you use heat exchanger, because sometimes we want to continuous. We want to make our product very more efficient, for example. So sometimes we use continuous sterile equipment. And this is the last example, holding time, which is this one. This is how they calculate holding time. Holding time for your sterilized temperature. Okay, what is sterilized temperature is required? Okay, liquid media is full at the rate. Okay, this is continuous by heat exchanger, which is this one, and sterilizer, the medium. Okay, this is what we want to eliminate. Spore concentration of this one. Okay, wow, value. Okay, this is for the thing, Arrhenius constant, and then this is activation energy. Contamination list survive over 60 day operation. Okay, okay, we need to clean everything inside the system. This is media density is nearly the same as water. Then this is viscosity as well. Okay, we want to find the temperature. The desired level of cell destruction is based on 60 day, ignoring any death in the heat and cooling section. The number of cell enter. Okay, 60 day. N1. This is flow rate. Okay, and this is what? This is the spore, concentration of the spore. Okay, this is a rate. This is spore, and then this conversion. Okay, the accept cell living during period is 1 over this. Okay, N2 is 1 living, N2 is 1. Okay, wait, N2 is 1. Okay, this is N2, right? N2, this one, this is N1. N1 is the beginning, so N2 is living. Okay, this one. Okay, we use cross-sectional area to the pipe, and then we have this one. This is the area, this is velocity, and then we calculate Reynolds number, which is turbulence, and then we use this figure, and then we have this value, dz, and then we have Peclet number, which is 370, and then we have this one Peclet number corresponding to dA is equal to 42. And for this equation, 14.102, and then we have KD, which is how we calculate the depth. Okay, and then put in this Arrhenius equation, and then we try to find the temperature, which is nearly 400 Kelvin. And after that, you can see the temperature that we require to sterilize this system is 125 degrees Celsius. With certainly we need to have more than 1 atm pressure. See, you have idea here, and then we confirm with the calculation that we need at least 125 degrees Celsius. This is for heat sterilization. Sometimes some liquid is very fragile or very sensitive to the temperature, so we cannot use temperature to sterilize. We need to pass to the filter, which sometimes is very expensive. And then this is the pore size of the filter. We might use very small pore size, like 0.22 micrometer, because we get rid of all the bacteria already if we use this one, and some viruses can pass through. So you can consider what pore size that you need, and then if you just want to get rid of some bacteria, so you use this 0.22 micrometer is enough. Or sometimes it depends on your application, and again the virus can pass through this very small size as well. Okay, this is toxic, and the number of bacteria in the air is order of this one, 10 to the 3 and 10 to the 4 per cubic meter. Okay, in the filtration is also common in large scale bioprocesses. Okay, and we don't use heat a lot for the gas because it's not practical. Okay, is typically the depth between fiber is 2 to 10 micrometer. Okay, and most of the bacteria is already removed. So for the final part, so if we want to use the bioprocesses for the longer time for sustainable, we want to saving energy, we want to save water, some utility, we want to minimize using raw material, minimize greenhouse gases emission. We don't want to generate a lot of pollutant. For example, this is how we design. No, okay. At the past, we just want to produce something, but for the next generation, we need to consider in the sustainable way to make our life stay longer and then cause less pollution. And we come to the end of this lecture already. I hope that you have some idea how bioreactor can contribute to produce some product. And I hope that you enjoy the course so far. And you might see me again in many courses in chemical engineering in Ubon Ratchathani. Hope to see you again. Enjoy my class. Bye bye.